In representation learning, we would like to learn embeddings that are useful for downstream tasks. Particularly, we need semantically similar embeddings to be closer or clustered together, and the geodesics between embeddings to be meaningful. In most cases, Euclidean geometry is used as the default solution. A large chunk of machine learning and deep learning pipelines assume Euclidean geometry due to its simplicity. However, there are many constraints of Euclidean geometry. It cannot embed large classes of graphs without distortion, and can only model intrinsically flat manifolds. Also, the volume growth in the Euclidean space is polynomial with respect to distance. However, the natural world is full of hierarchies. Therefore, representation learning in the hyperbolic space provides many advantages. Embedding unimodal text and image embeddings in the hyperbolic space has been explored in the literature. However, we focus on multimodal representation learning in the hyperbolic space in this work, which is relatively less explored. The conventional spatial proximity-based contrastive loss in the Euclidean space can be directly extended to the hyperbolic space as well. To this end, we can just maximize the hyperbolic inner product between paired embeddings, which is equivalent to minimizing the hyperbolic geodesic distance between the paired embeddings. However, this methodology can disrupt unimodal and cross-modal hierarchies. For a more comprehensive analysis, please refer to our paper. In our work, we argue modality gap is rooted in intrinsic differences between the modalities, and trying to close this gap using in spatial proximity-based contrastive loss can result in subparstructure in the latent space. So, we ask the question, can we accept the modality gap in representation learning? What if we use an alternative measure of similarity to align embeddings across different modalities? This prevents the image embeddings from being collapsed together spatially, and allows an extra degree of freedom for them to demonstrate the hierarchies. To this end, we propose a novel hyperbolic angle-based contrastive loss. In this loss, the similarity between the paired embeddings is measured using hyperbolic angles, and we allow the embedding norms to be varied, and implicitly enforce cross-modal hierarchies such that text is always more generic than images. We show that our model achieves state-of-the-art results in classification and retrieval tasks in the hyperbolic space. This is an example of text-to-image retrievals. The retrieved images are arranged left to right according to their distance from the origin. As evident, the images get more and more definite with respect to the text, as the embeddings get further from the origin. We also explore implicitly learned abstract to specific hierarchies. To this end, we embed eigenfaces and actual faces on our learned space, and estimate the geodesic distance of the embeddings from the origin. Compared to the baseline, our model shows a clear hierarchy in this scenario. We also explore part-based hierarchies in images. As shown, we outperform the baseline by a clear margin. We also explore image-to-text retrieval hierarchies. The baseline also preserves some hierarchy in this case. However, our model is able to obtain better results in this case also.